All right, so this is the second example that we had from the friction lecture. And just to refresh your memory, we have a applied force P imparted to a wedge A. That wedge A is going to be pushing up on this stub. The stub has a spring compressed above it, and A is also pushing against this ground surface B. We're given some information about the spring. We're told that it has a stiffness of 300 newtons per meter. We're told that it has been compressed 60 millimeters. And we're told about the friction interface between A and S, that wedge A and the stub S. It's at 0.5. And the friction interface between A and the ground surface B. And that's given with a coefficient of friction of 0.4. And we're asked in this problem to figure out what is the minimum value of P to cause that wedge A to move to the right. And so this is a typical kind of problem where we're asked to solve for the force to cause motion to occur. But really what we're focusing on is what is the static friction that needs to be overcome and what force P will be able to impart that to the wedge. So even though we're talking about movement, what we really care about is what is that point right before movement is caused, and that'll be the maximum Coulomb static friction. And that's why we can use this mu value. That's the maximum value of friction before motion is imparted. So to do that, we need to start looking at free body diagrams, and with most of the other problems, we just need to start making section cuts to really define our free body diagram. So my first section cut, I'm going to isolate that stub S. For the second section cut, I will cut right through the interface between A and B, right through the interface between S and A as well. So I'm going to need two different free body diagrams to fully describe this. And so the stub and the wedge. I'm going to simplify what the wedge looks like to a certain extent. Okay, and this is wedge A, this is stub S. And I need to look at all of the forces acting on each of these surfaces, and we'll just kind of start from the bottom, start from the top and go to the bottom. And I'll use a consistent coordinate system for these, just our standard X positive to the right, Y positive going upwards. I'm going to have a force acting down on the stub due to the compressed spring at the top of S. And so the force in that spring, because the spring is compressed, it's going to be pushing against any surface it is connected to. And so that's why I point it downwards, and it'll be equal to K times delta, which is simply equal to 300 newtons per meter. And I need to make sure that I'm good with the units here. Delta is given in millimeters. I need to change that to meters, so that's 0.060 meters. And so I'm going to get 18 newtons. I have no forces on the sides of the stub in the given. I didn't draw it here, but there's kind of a guide or a cylinder that the stub is acting in. But the problem statement tells us that it's not rubbing up against those sides, so there's no friction on the sides. But there definitely is going to be some force interface between this inclined plane and its complementary side on A. So here we're going to get a normal force acting on the interface. So I'll call that NSA. And I can even just start drawing that on the other free body diagram as well too. I will get NSA acting on the complementary side. And to figure out which direction to assume for the friction forces, I think it's also helpful to draw the imposed force as well too. So P is pushing to the right. The call of the question asks us to figure out how much P is required to get A to move to the right. And so our friction forces need to be predominantly in the direction to oppose that. So the friction force on this wedge is opposing that movement to the right. And so that friction force on interface SA is going to be pointed predominantly to the left. Now I understand part of it's going vertically, but here if movement's to the right, it would need to be pushing back to the left. The same thing down below, we have some normal force on this interface AB, and the friction force will be opposing that motion that's stipulated in the problem to the right, which means that the force needs to be going to the left. So this will be the friction force on that same interface AB. And so then if I know that on the block, the friction force between the block and the stub is going to the left, then on the complementary side, on the stub itself, it's pointed to the right, and that'll be FSA as well. Now we're missing a little bit of information here that's going to be critical to this problem. So we're not given any of the geometry of the stub or of the block A in terms of like the width, the length, and things like that. But we are given information about some of these angles. So this angle right here is 30 degrees, which means that the angle of the friction force is 30 degrees from the horizontal, which is important. Which means, likewise, that the normal force has to be the complementary angle, which will be 60 degrees. And that'll apply both to either side of that free body diagram. Same thing here. This is going to be 60 degrees. The bottom, the interface between A and B, is shown as horizontal. We can assume that the spring force and the applied force are both vertical and horizontal respectively. But other than that, this should be enough information for us to solve for everything. Now, if we start looking at the unknowns here, I don't know P, I don't know NAB, I don't know FAB, I don't know FSA, I don't know the normal force in that same interface, and I do know the spring force up at the top. I can calculate that it's based off K times delta. So I don't know 1, 2, 3, 4, 5 of the values. Now, here it's a little bit tricky because if we say that we have 5 unknowns, you might quickly say, well, I have 3 equations of equilibrium for the top free body diagram, and I have 3 equations of equilibrium for the bottom free body diagram. And that is not the case here because this has a trivial equation, which is the sum of the moments. So if you'll notice, we talked about we didn't have any information about the height or the width or any of the lengths on these members. All that we're given is just the angle. So you can almost think of this as like a method of joints type problem where we're not given enough information to make the summation of the moments a non-trivial solution. So here I might want to write down some of the forces in the x equals 0, some of the forces in the y equals 0, and some of the moments equals 0, but that sum of the moments equation doesn't do us any good because we're not given enough information to figure that out. So really we're talking about like these are idealized as single points in space, but it's still enough for us to be able to solve for everything. So with this in mind, with the moment equation being trivial, what we're really talking about is 2 equations of equilibrium up top, just sum of the forces in the x equals 0, sum of the forces in the y equals 0, and again the sum of the moments is trivial because there's no dimensions given to be able to calculate a moment from. And so I get 2 from the top, I get 2 from the bottom, I get 4 equations of equilibrium, but again we said that we have 5 unknowns. So I need to be able to get this down to a reasonable number of equations or a reasonable number of unknowns. And what I can do in this situation is I can say, well, in order for A to move to the right, I need this interface to slip SA, and I need this interface AB to slip as well too. So if this is a rigid body, so if one part of it slips, the other one has to be slipping as well too. So in this case, I'm actually going to be able to set FSA as equal to mu SA times the normal force on that same interface, because this is going to be right on the verge of slipping. At the same time, FAB I can rewrite as mu AB times NAB, because if this is slipping or right on the verge of it, so does this interface need to be. And so really I get 2 equations based off mu times n So really in this situation, I have 5 unknowns and I have like 6 equations of equilibrium. So let's just go ahead and run through the math. We're going to have more than enough equations to be able to solve for what P is equal to. And so let's just go ahead and start doing that. So the order in which we go about writing our equations of equilibrium is completely up to you. You're not going to get an incorrect answer if you start with the wrong equation. You just might not be able to get to the full solution right away. So let's just start writing out these equations. So I can choose to either like start up here, or I can start down below. Now, if I start up here, I'm going to have just just really one unknown here, because the friction force on SA is equal to mu SA times N SA. And so that's one place to start from. I could solve for NSA directly that way. I could also just start down here, because really I have like 1, 2, 3 unknowns. But I think starting up here, then working our way down, because we really only have 2 equations of equilibrium. So starting with this block that has 1, 2, 3 unknowns, I'm not going to be able to solve for that with just statics alone. So we've got to start up top first. And so I'm going to sum the forces in the y direction equal to 0 with my top free body diagram, and that's going to give me 18 newtons going down. That's going to give me NSA times the sine of 60 going up, so plus NSA times sine of 60 degrees. That's going upwards. That's the vertical component of the normal force. And then I get the friction force going downwards. Again, the friction force is simply equal to mu SA times N SA, and then times sine of 30 to get the vertical component, times sine of 30 degrees. And here, sine of 30, I can calculate that. NSA I don't know yet. Mu SA is a given value. Mu SA is given as 0.5, so I can change that to 0.5. NSA we don't know yet, and sine 30 we can easily plug into our calculator. We get 0.5 for that. But fundamentally, I only have one unknown in this equation, which means that NSA can be solved, and in this case it's equal to 29.22 newtons. And as a corollary, if I want, I could also solve for the friction force as well too, because the friction force along that same interface is simply equal to mu SA times NSA. I can plug in my values of 0.5 and 29.22 newtons, and I get that the friction force acting on that block is 14.61 newtons. So from the upper free body diagram, because I only had one unknown, I was able to solve for it using just statics. And I get the normal force, and as a result, I can also calculate the friction force as well too. So I'm just going to move those over to the side here as things that we know. I know NSA equals 29.22 newtons. I know FSA equals 14.61 newtons. And then I'm going to go ahead and erase this just to create some more room to now deal with this free body diagram here. Because this free body diagram, the unknowns are P, NAB, and NSA. The friction forces are just determinate based off the other ones. It has 3 unknowns, but I just calculated NSA, which means that I'm really only left with NAB and P as my only unknowns. So now that I've dealt with that up here, I can move it down here, and I can solve for P pretty quickly. So if I do that, P will only show up in the horizontal equilibrium equation. Sum of the forces in the x direction is equal to 0. And I get P going to the right, my positive x direction, Here I have FSA going to the left. It's inclined at 30 degrees, so I've got to multiply it times cosine 30 to get it acting in the pure x direction. So minus FSA times cosine of 30 degrees. Again, I already know what FSA is. I calculated it up above, so that's 14.61 newtons. NSA, that normal force, is also going to have a horizontal component that I'll get by cosine of 60. It's also pointed in the left direction, so it'll be negative. So minus NSA times cosine of 60 degrees. We've already calculated NSA as 29.22 newtons. I'm not quite done yet. I've put P and then these two forces on there, which I already know. I need to now put FAB, and that'll be minus FAB, but we know that FAB is simply mu AB times NAB. Mu AB being 0.4. Okay, so I'm not quite there yet because I've got P as an unknown and I've got NAB as an unknown as well too. So one equation, two unknowns, I'm not quite there yet, and because I can't use a summation of moments because there's no dimensions given, I can't solve for P with one single equation quite yet. But I just need to rely on my other equilibrium equation, that is the sum of the forces in the y direction equal to 0. And in that case, I get FSA. It's inclined 30 degrees. The vertical component would be times sine 30. So it's FSA times sine of 30 degrees. Just like before, I know what FSA is. In this case, it's 14.61 newtons. NSA is going downwards, but it's inclined. The vertical component will be sine of 60. So I get minus NSA times sine of 60 degrees, but we know that NSA equals 29.22 newtons. And then the only other value that I have here is NAB, and NAB is going upwards, so plus NAB. Now, I should have started with this one first, but it's fine that I didn't, because in this equation, the only unknown that I have is NAB. And this tells me, if I do my algebra, NAB is equal to 18 newtons. So NAB is equal to 18 newtons. All that I have to do is plug it back into my summation of the forces in the x direction equal to 0 equation, and then that will tell me that P is equal to 34.5 newtons. So just like I said at the beginning of the problem, you oftentimes may have to solve for simultaneous equations. In this case, technically you didn't need to, but me guessing that the sum of the forces in the x direction was the best way to solve for P turned out to be incorrect because I ended up with two unknowns, but it didn't derail me. All that I did is I left that equation unsolvable. I went to the next equilibrium equation, sum of the forces vertically. I solve for NAB, and then I just go back, I plug it into my original equation, and now I only have one unknown, which would then allow me to solve for P. So again, I know a lot of students get kind of frozen and they say, well, I don't know if I should sum the forces in the x or in the y or do moments if that's available as well too. It doesn't matter. It won't give you the wrong answer. It just might get you to the point where you need to rely on another equation and then plug back in the value a little bit later on. So don't be afraid to write any equilibrium equation as you want. As long as it's accurate based off your free body diagram, it won't give you a wrong answer. It just might require another step to solve for it. So again, keys to this problem. The free body diagrams are critical. Showing the friction forces and the normal forces across an interface as equal and opposite are crucial. Here, recognizing that the interface between S and A will only slip if the interface between A and B are slipping at the same time, because they have a similar rigid body that they're both connected to. That's the key to this problem. You wouldn't want to assume that A is slipping, A to S is slipping, and A to B is not. That wouldn't be possible, and that's why each of these friction forces are set to their maximum based off the mu values, the coefficients of static friction that we're given. So those are kind of the two big keys. Make sure that you're drawing your free body diagrams completely. And one thing that I didn't do here, because I didn't have a lot of space, is it might have been helpful to draw each of these inclined forces in their y component and their x component on the free body diagram, because when you get to this point, putting cosine 30, cosine 60, things like that in your equilibrium equation, it's really easy to mess up sine and cosine between the free body diagram and your equilibrium equation. So I recommend doing it on your free body diagram and then making sure that you give yourself enough space. So again, this is essentially like what I would call a ladder problem, because it simply involves section cuts around the interface of each of these discrete members. And so this is this step right here. I see a friction interface, so I need to put a section cut through there, a friction interface down here, so a section cut through there. Up top, I make a section cut through the spring as well. And then I draw a free body diagram of each of those. And so that's the same thing that we were doing with the ladders. The fact that this is a wedge doesn't really change the equations. It's just a different structure type to look at. But it's not like a belt where you need a special equation to figure out what the friction is. It's not like a screw thread where you need a special equation. This is still the same fundamental. Draw your normal force and your friction force along whatever interface you have. Maybe you have to split up into multiple free body diagrams, but the equations are all fundamentally the same.